Let's review the general steps we went through in analysing a two-level atom coupled to the optical field. We started off with a simple Hamiltonian. So we have our two-level atom and we have large numbers of modes of light that it can interact with, and we also considered the situation where we had a laser shining on it. Now we start by getting the Hamiltonian. Now we know the Hamiltonian for the atoms, we know the Hamiltonian for the light, and we know the Hamiltonian for their interaction. There's a large number of modes there, but with the exception of the single mode, which is the laser mode, all of them starting off in roughly the vacuum. In general, it might be a thermal state where there might be a couple of stray photons, but it's pretty close to the vacuum. So we know how to trace over those modes and generate an evolution equation for the reduced density matrix describing just the laser light and the atom, where again this super operator is defined like that. Now the energies of the atom and the light themselves give us one set of basis states. So if we look at the eigenstates of just that part of the Hamiltonian, we end up with a manifold of states. So we've got all the ground states and all the excited states. And the spontaneous emission term, which is what that is, that's the term that describes all our coupling out into those vacuum states. What that does, this operator here, is very simple. What it does is it takes us from the excited state down to the ground state. That's exactly what this will do. So it just takes these states down to their appropriate ground state, excited state down to ground state, without changing the number of photons. You'd think there'd be a photon spat out, and there is, but it's spat out into the vacuum. These photons here are the number of photons in the laser. Okay, so the spontaneous emission doesn't change the number of photons in the laser. So clearly this basis makes an excellent choice for describing what the spontaneous emission is doing, but you'll notice we've chosen a basis where we've looked at the eigenstates of a fraction of the Hamiltonian. Now in fact, these states are usually called the bare states, and when we include the effects of the interaction term as well, and the interaction term couples pairs of levels like that from the bare states, then of course we're going to get a whole different set of eigenstates, and those eigenstates we're going to call the dressed states. And we're going to have the same number of them because they're a basis, and they're going to naturally come in pairs, and they're just going to be linear combinations of our pairs of bare states, and so we're going to end up with a manifold that looks like. And because each of these states contain both the excited and the ground state, then the spontaneous emission term in that is going to couple both out of them and into them. And so we're actually going to get three different kinds of spontaneous emission. We're going to get our normal spontaneous emission with the normal frequency, and we're also going to get a low frequency spontaneous emission and a high frequency spontaneous emission. The idea of three different frequencies of light coming off a single two-level atom with a particular energy resonance being driven, for example, completely on resonance seems kind of odd. Where does that extra frequency come in? We know where this frequency comes from because that's both the energy of the photons in the laser and it's exactly the same as the energy difference between the two levels in the atom. But where do these two come from? Well, of course, the other energy scale in the system is precisely this difference here, this energy difference between the two dressed states. So these two things, when you're on resonance, are exactly the same energy when you ignore the coupling, but when you turn the coupling on, the energy splits. And the amount that the energy splits depends on the number of photons in the mode, and therefore it depends essentially on how hard you drive your two-level atom with your laser. So as you drive it harder and harder, you'd expect those three lines to get further and further apart. And indeed, that's exactly what you see in experiment, where you do a resonance fluorescence experiment. You see what's called the Mollo triplet. So you get three very well-defined peaks in your spectrum, and the harder you drive the spectrum along this direction, then the further apart those peaks get. So this system is one example of a system in which it's much easier to understand what's going on if you think about the dressed states rather than the bare states. Any basis is as valid as any other, but our intuition works better in some compared to others. Now it's fairly unsurprising that the dressed states are often a very good basis to think about because they're the actual eigenstates of the Hamiltonian. And there are many other systems where we see rather unusual looking behavior that seems far more reasonable when you think about the dressed states. Another example is the atom laser. An atom laser is a coherent source of atomic waves, of matter waves, that you can get by coupling atoms out of a Bose-Einstein condensate. Remember, a Bose-Einstein condensate is where you have all the atoms in the ground state of some kind of trap, and therefore they have exactly the same kind of properties you might expect from a lasing mode. Now those trapped atoms will typically have some magnetic submanifold where they have different MF states, and those different MF states will experience typically different potentials in the magnetic field. And so in a particular magnetic field, we might be able to trap some states while anti-trapping others and having no effect at all on the others. And so the trapping potentials are going to look something a bit more like this, where the real potentials have even more symmetry than my hand-drawn diagram does. You can see that for the MF equals 0 state, we still have the gravitational potential on, and so all of these potentials have the gravitational potential plus the magnetic potential, which is why the bottoms of these two trapping potentials are offset, and same with these two anti-trapping potentials. So all we need is our spatial degrees of freedom, which in this case is just one spatial dimension, and our MF state, and we've got our Hilbert space for our system. And the Hilbert space has these basis states. And if we know the basis states for our Hilbert space, then we can write an annihilation operator for each of those. And the annihilation operator just has the same indices. And then we can write down the Hamiltonian and know what happens. And the Hamiltonian is going to have a kinetic energy term, these potential terms, some nonlinear interaction terms between the particles, and finally the explicit coupling that we put on. So we might make some radio frequency transitions to transition between these states. And of course that gives us a large and intractable quantum field theory to solve. So instead we make the semi-classical approximation where we assume all the modes are in a coherent state, and that coherent state is indexed by this phi. And then we get our semi-classical equations of motion just from the Heisenberg equation of motion for the field operator and taking the expectation value, and we get the following. So that's just a 5-component differential equation with one spatial dimension. So we could certainly put that on a computer and solve it. We could put our spatial dimension onto a grid and we could solve that numerically. However, before we do something like that, it's always a good idea to try and figure out what we might expect to happen. Now these couplings here, these omegas, are all caused by the radio frequency radiation that we're going to be applying to the atoms in order to get the transitions between the magnetic sublevels. And those coupling terms are going to oscillate at the radio frequency. Now we can certainly deal with oscillating terms in our equation of motion, but things are often a lot simpler if instead we go into a rotating frame and make those terms static, and that can be done just by defining new variables. Instead of having these phis, we have these phis that rotate at different rates. And by choosing those frequencies appropriately to the different MF levels, we can simply go into a frame where all those omegas do not rotate anymore. And what that's going to change is it's going to change the potentials. And in that rotating frame, all of those potentials will have the same value at precisely the spatial point where the radio frequency was resonant with the transitions between these different states. Apologies for that diagram, but they don't look particularly resonant at the same place, but in fact they are. Incidentally, you can make exactly the same transformation back in the full quantum theory by going into the interaction picture. So what do we expect to happen? So supposing we were to start with a large number of atoms in this trapped state. So they'll be maybe in the ground state of that, all trapped. And then we turn on the coupling. We turn on the coupling such that it's resonant at some point here. What do we expect to happen if we wait a large amount of time?